Welcome back to Calculus 2. This is video section 1.4 on elementary integrals and the net change theorem. Elementary integrals is essentially the notion of antiderivative. In Calculus 1, you go over differentiating functions. And at the end of Calculus 1, you then say, oh, we know how to differentiate functions. Let's view things in the opposite order. And the resulting value that we get, call that an antiderivative. So here's an example. If we take this quantity on the right and differentiate it, we know that we produce the integrand c. Capital C is a constant. It differentiates to 0. Cx differentiates to c. So this right-hand side is an antiderivative for the integrand. Note that when we have an antiderivative, we have a family of functions, as this capital C can be anything. Now that we're doing integrals, we would say that anytime we evaluate an indefinite integral, we always pick up a constant of integration. Good. Let's look at some other elementary integrals. Back in Calculus 1, the power rule tells us that when we differentiate the variable to a power, we bring down the power and decrement the power. Doing so, we've just verified that the derivative of this expression produces the integrand x to the n. Now, this is an elementary integral, which holds anytime we have x raised to a power, with the caveat that the power cannot be -1, as dividing by 0 is not allowed. All right. Let's go back over. How do we evaluate an indefinite integral of x to the power n? We increment the n by 1 and then divide through by that new power. And as it's an indefinite integral, we always pick up a constant of integration c. Okay, so let's look at the special case when n is -1. Well, we can recall that the derivative of the natural log is 1 over input. And you always want to be careful. You don't know whether this x is positive or negative. Thus, when you write the right-hand side, you always want to include the absolute values. Very good. Tied in with the natural log is its inverse function, the natural exponential, which has as derivative itself. Thus, the indefinite integral of the natural exponential is just itself plus the constant of integration. Good. Another basic function is sine and cosine. Differentiating sine produces cosine. Thus, the indefinite integral of cosine is sine of x plus a constant c. Okay, if we flip that around and are looking for the indefinite integral of sine of x, we know that the derivative of cosine produces a minus, so we prepend that function with a minus sign. Very good. Derivative of tangent is secant squared, thus the indefinite integral of secant squared of x with respect to x is tangent plus a constant. Let's do one more. The indefinite integral of secant of x tan of x is secant of x plus a constant because the derivative of secant is this integrand. Very nice. If you open the book, you can find a more complete list. And in the book, they will give you the derivative, which you can recall from Calculus 1, and then its restatement as an elementary integral. Good. So that's elementary integrals. Which was a restatement of antiderivatives in a sense. So too is the net change theorem. It's a restatement of the fundamental theorem of calculus, part 2. Let's take a look. So here is the statement of the net change theorem. A function, capital F of t, is produced by adding an integral of its rate of change, so that's capital F prime, to its initial value. All right, so this net change theorem is geared towards applications. So if we have a function, something that's changing, it's changing from some initial value. And if it had an initial value, suppose that occurs at some time t naught. Then at that time t naught, this expression capital F of t naught is the initial value. Then you're interested in, well, what is the value of this function at some later time t? And that can be found by adding to the initial value the integral, and this is a definite integral, from the initial time out to the time that you're interested in, with integrand the rate of change of this function, capital F prime. Then the s is the variable of integration. It is a dummy variable, the s. Good. Now if we move this initial value to the other side, then this form looks a little bit more like FTOC Part 2. So these two equations are equivalent statements. All right. Do an example. Let's go over this notion of net displacement. In Calculus 1, you might have studied rectilinear motion. And in rectilinear motion, it's common to use little s of t as the position function. Putting a delta in front of that, so delta s, the change in s, or the change in position. And that's just looking at the starting position and its difference with the ending position. Also, little s of t, taking its derivative, its rate of change, position's rate of change is velocity. So suppose that we have a position function which has rate of change, velocity, v of t, given by this linear function, 5t minus 20. And then under this velocity function, let's find out how position changes from time t equals 0 to time t equals 5. Okay. So if we use that the change in position s at 5 minus s at 0, that'll be given by the integral from the initial time to the ending time of integrand the rate of change of position, which is v. And then v is a nice linear function. 5t integrates to 5t squared over 2. Negative 20 integrates to negative 20t. This is a definite integral, so we know how to evaluate it. We plug in the top, subtract away plugging in the bottom. Doing that, plugging in the bottom is going to produce 0. We don't have to write it down. And then we get a value. So the net displacement, delta S, is negative 37.5. Let's relate this back to area. Here we have a nice little graph. We're plotting the velocity function over inputs from 0 to 5. The velocity function is a linear function. The slope is positive 5. The y-intercept is negative 20. Y-intercept negative 20, positive slope of 5. Therefore, this line is the velocity. And notice that the velocity is passing the t-axis, that would be t equal 4. And that we have two triangles, one shaded in red to represent a negative, and one shaded in blue to represent positive. All right, here's a nice little assignment. Reusing this velocity function, now determine the time t tilde such that the net displacement will be 0. In our example, we had net displacement of negative 37.5. How long do you have to wait from time t equals 0 to time t equal t tilde such that the net displacement is 0? Very good. Do another example. We're going to reuse the same velocity function. And we've dealt with net displacement. Let's now think of total distance traveled. So net displacement, if you're at home and you want to have your favorite drink, but you're out of it, you have to go to the store, procure it, and then return back home. Well, going to the store is traveling, coming back home is traveling, but your net displacement would be 0. Total distance traveled is some positive value. So let's again reuse the inputs 0 and 5 and see how much distance is traveled. Well, it's a simple matter of placing absolutes on the velocity function. And if we recall, we took the difference of 40 and 2.5. So now we would take the sum of 40 and 2.5 to get a total distance traveled of 42.5. So that's arguing off of the graph geometrically. So here that red triangle has been flipped in the t-axis to be a blue triangle, and then we're just adding those two areas. More analytically, this 40 is produced by taking the integral from 0 to 4 of the absolute of v of t, whereas the smaller triangle with area 2.5 is given by the integral from 4 to 5 of the absolute of v of t. Compare the two integrands, and v of t over the interval 4 to 5 is exactly 5t minus 20. But v of t over the interval 0 to 4 is 5t minus 20, taking negative values. So the absolute of that would be place a minus on everything. Good. So here's a different velocity function. The rational function t squared minus 4 over t. Initial time, let it be 1, and terminating time 3. And for that setup, compute the net displacement and compute the total distance traveled. Excellent. So we've done two review topics: elementary integrals, essentially antiderivatives, Net Change Theorem, essentially the fundamental theorem of calculus part 2. Now let's look at integrating even and odd functions. So let's recall, well, it looks like we're sketching the graph of a parabola, x squared, and a cubic function, x cubed. And then let's think about behavior of squaring an expression negative x squared. Properties of exponents allow us to rewrite that as negative 1 squared times x squared, but negative 1 squared is just positive 1. Try that with the cubic. The expression negative x quantity cubed would become negative 1 quantity cubed times x cubed, and negative 1 quantity cubed is negative 1. All right. So, taking these algebraic manipulations and relating them to their corresponding graphs on the power 2 parabola, its graph has nice symmetry with respect to the y-axis, meaning that if you pick a point on the parabola and reflect it across the y-axis, you produce another point on its graph. Same idea on the red curve, which is the curve of x cubed. If you pick a point on the red curve and reflect through the origin, then you'll produce another point on its graph. So this idea of reflection, we're looking at two different types of reflection, either symmetry with respect to the y-axis for the blue parabola, or symmetry with respect to WRT is with respect to the origin on the red graph. Good. And we'll make a definition that if you have a graph of a function that has symmetry with respect to the y-axis, like the blue parabola, we'll term that an even function. And this is pretty easy to remember if you think of the parabola. The exponent is an even power. Versus the cubic, the exponent is an odd power. And that's exactly what we'll term any function that has symmetry with respect to the origin. We will term it an odd function. Very good. Next, we're going to make algebraic definitions. And notice that here, when we evaluate the function on negative x, we get the same thing as the evaluation of the function of regular x. But for the odd function, when we evaluate negative x, that negative comes out into the front of evaluation on the regular function. Let's look at the next slide and see that. So here we go. We were just looking at some graphs. Let's now make definitions of even and odd functions in terms of algebraic statements, and say that we have an even function, so that's the parabola. If we evaluate the function at negative x and we get the same output value as the function at just x, and that a function is odd if, when we evaluate f at negative x, we produce a value which is the same as the opposite of f at x. Beautiful. Now, you know other instances of even and odd functions. So you want to think of the graph of cosine. And we have a little animation that we're going to watch. But over here, we're looking at a definite integral from negative a to a. Okay. And you want to think, all right, well, the integrand is an even function. And then let's take a look at an animation. So the black curve is the curve of cosine. And then we're shading under the curve to the right in blue from 0 to a, and in green to the left from negative a to 0. Let's watch that again. And what you want to notice is that the amount of area shaded in green matches the amount of area shaded in blue. So if you're trying to compute the definite integral from negative a to a, you can get away with just computing, instead of both green and blue area, just the blue area and double it up. So that's what this expression is. All right. Let's contrast that. That was for an even function. Let's contrast that with an odd function. So we're going to watch an animation. We'll have two shadings. To the right of the y-axis, to the left of the y-axis. And for sine, the amounts are the same, but they're of different signs. One is positive and one is negative. And note that we're taking symmetry about the origin. So in other words, from negative a to positive a, that the amounts above and below are exactly canceling each other out. Thus, if you have an odd integrand and symmetry in the bounds, negative a to a, that the evaluation of this definite integral is straightforward. It's just 0. All right, let's write that down for generic, even, and odd functions. You want to look at the integrand. Identify, is that integrand even or is the integrand odd? And then if you're in that case of even or odd integrand, maybe you can get lucky and have symmetric bounds in negative a to a. If it's odd, then the evaluation is super straightforward. You just get 0. But even if it's even, you still get a little bit of help. You can double up and only evaluate from 0 to a. The benefit is that the algebra is made simpler because evaluation at 0 is typically straightforward. Beautiful. All right. Nice assignment. 2 integrals to evaluate. The first one is just compute out a value. Elementary integrals. The second one doesn't look like it can make use of even and odd functions, as you should verify that the integrand is odd, but the bounds don't seem to have symmetry at first glance, but in fact, they do. So verify that the bounds have nice symmetry and evaluate in a straightforward manner using properties of even or odd functions. Fantastic. That ends section 1.4. Thank you so much for watching. I'll see you on the next one.